Okay. Okay, I hope everyone is back from GatherTown. This is the last but not least talk of this session, but also of the whole conference. And we actually have the pleasure to have Gina-Ann Incorvia, assistant professor at the University of Texas, who also holds the fellow, and it's a fellow of advanced micro devices chair in computer engineering, Department of Electronical and Computer Engineering at the University of Texas. She directs the Integrated Nanocomputer Lab. Professor Incorvia develops nano devices using emerging physics and materials for the future of computing, including neuromorphic computing, in-memory computing, bio-inspired computing, and computing in extreme environments. She received her bachelor's in physics from UC Berkeley in 2008 and her PhD in physics from Harvard University in 2015, cross-registered at MIT. She completed a postdoc at Stanford University before starting at UT Austin in 2017. She has received the 2020 IEEE Magnetic Society Early Career Award, the 2020 U.S. National Science Foundation Career Award, and is a 2020 Intel Rising Star. So, Jinan, it's a real pleasure to have you here. Please go ahead.
Okay, you can hear me okay?
Yes.
Wonderful. Well, thank you so much for the invitation, the introduction, and for continuing to host this fantastic conference. I know it was kind of inspired by the pandemic and connecting our community around the world, and I'm just really happy to see that it's continuing and thriving. So yeah, I'm happy to be here to talk about our work, my group's work on using magnetic spin textures for cognitive computing. So this is a collaborative effort with the authors are listed here. So it includes the students in my group. Also, Priyambada Jadun was a postdoc here at UT Austin, is currently at IMEC. Our collaborator, Joe Friedman at UT Dallas, and then our collaborators at Sandia National Laboratories, and also a collaborator in the neuroscience department here at UT. So just to introduce my group, since you mentioned it. So my group is called Integrated Nano Computing Lab, and we really have a materials to device vertical approach to changing how computing is done using new materials and new physics, which I think this community is very familiar with. So I'm just going to go through a brief introduction and motivation for magnetic-based computing beyond memory. I think this is a topic that we're all familiar with, but it's good to see this motivation and think about it. And then I will go into our results on building robust Dewey-Wall magnetic tunnel junction devices for these beyond memory applications. I will then go into one particular application of these devices for magnetic synapses and show that we can, by tuning the device itself, we can have device inherent behavior that can be bio-inspired and application specific, and it can have system level benefits. And that's kind of the goal of this type of research. And then I'll end the talk with some touching on simulations of maybe instead of Dewey walls using skyrmions for these biomimetic neurons and what skyrmions can provide us. So we are in a new era of computing for artificial intelligence that uses deep neural networks and Beyond-Von-Neumann architectures. So this has been going on for a while, but more recently, we are at a really exciting opportunity to inject new materials, for example, magnetic materials, into these really exciting new paradigms. So here's just on the left is a cartoon of these multi-layer neural networks. And on the right is a cartoon of the type of circuit we work with, where we can have the vectors coming in that are representing data. We can have error vectors that are doing error correction and tuning the weights of our magnetic synapses. So neuromorphic computing uses artificial neurons and synapses in neural networks and in other architectures. So the basic building blocks are neurons that integrate incoming signals and activate, and synapses that connect neurons. So they should be multi-weight and non-volatile. And so neuromorphic computing can be implemented with CMOS today, for example, in spiking neural networks, and two actively used examples are IBM True North and Intel Luihi. And they're making great progress in using these platforms for things like robots being immersed in the environment and recognizing images. It's really exciting, the new things that are coming out just using CMOS. But at the same time, artificial intelligence today faces clear challenges. So it lacks the advanced cognition that we know human brains can have. It's not very adaptive yet or responsive to surroundings. It doesn't innately have a lot of context. And it's hard to have like a coherent representation of the world like we can have very easily in our brains. It's also very energy intensive in both training and inference. So when we look to the next generation of AI, this is where new materials and Spintronics can really play a big role in pushing AI into these new areas. And to get there, we really have to ask, what is the origin of advanced cognition in these biological systems that we want to emulate? And then how do we realize that using our new materials? So this is a magnetism talk today, magnetism workshop. So we all are very familiar with what magnetic materials can provide for this space. So magnetic materials have relatively low write energy and write time to switch them, especially for memory applications. They're non-volatile. They're back in the line compatible, so they can be integrated with CMOS. They are very hard to radiation, which is really exciting for space applications and extreme edge computing. And then really importantly, they have really interesting complex features that we can map onto these new systems. So things like domain wall dynamics, skyrmion dynamics, oscillatory behaviors, and magnetic stray field interactions. And so we can also see the success that MRAM's having. I don't need to go into this too much for you. So it has potential applications in memory. Okay, so just briefly, we're all familiar with these topics, but I want to just start out with the building blocks of what we can use for our neuromorphic applications of magnetic materials. So the first basic building block is the MTJ. And so I'm not going to go through this. I assume you know what MTJ is. So magnetic tunnel junctions have been used for standalone memory and embedded memory. And so when we look to these near-term applications of Internet of Things, wearables, extreme edge computing, higher areal density hard disk drives, and then these far-term applications in memory computing, artificial intelligence, and these neuromorphic and brain-inspired computing, we can see we really are going to need materials and device revolutions to get there. So the second basic building block that we can use for neuromorphic computing is the domain wall. We can propagate it. Here is a simulation and UMax of it moving around in this nanostructure. And the third building block is skyrmions, which we can also use in similar ways to domain walls, and also they have their unique properties. So I'm going to go back to this type of skyrmion neuron at the end that we've been working on. Okay, so this is a big field, and there are many groups working on this topic. So I just picked 4 papers here to highlight the breadth of this field. So there's people working on racetrack logic, stochastic, a lot of work on stochastic magnetic tunnel junctions, spin torque oscillators, and skyrmions moving through reservoirs and things like that. So it's a big, wide open field, a lot of opportunity. So the device I'm going to focus on for most of the talk today is the domain wall magnetic tunnel junction. So it looks like there's a cartoon of it here. So it's a simple extension of a 2-terminal magnetic tunnel junction where we extend out not just that bottom spin orbit torque layer like for SOT MRAM, but extending out the bottom free layer of the domain wall that could move in the bottom free layer that you normally would switch through the tunnel junction. Now instead we're switching the domain wall back and forth using spin orbit torque. So here our domain wall is shown as white here, and we can apply a current through in and clock and then drive it back and forth and then change the output of the tunnel junction. So what the domain wall really provides us here is an extra degree of freedom that we can control to have more dynamical effects in our SOT MRAM-like device. Okay, so let me go into building these. So for maybe 10 years or so, these domain wall-based devices were really facing challenges of high current density and low TMR. So at the left here was some example devices that my group made back in 2016 So you can see the resistance of the junction went from like 55 to 60 ohms. And then here was a paper from Intel and IMEC in 2018, and they show similar, like 15% TMR. And a lot of this is because unlike SOT MRAM, where you can etch to the fairly thick free layer on the bottom, sorry, very thick spin orbit torque heavy metal on the bottom, here we need to like precisely stop our etch right at the MGO without creating shorts and preserving this free layer as well. So this is one thing we sought to tackle in our group, and we were able to build these prototypes down to 250 nanometer feature size. So this is SCM images looking down on the devices. And so the tunnel junction is in the middle, and this is the width of the track. So this one was 400 nanometers wide, and the right one here is 250 nanometers wide. So these films were grown by Applied Materials, and then we patterned them into this 3-terminal domain wall magnetic tunnel junction structure at UT Austin. So the tunnel junction is in the middle. We also add this extra electrode here, and that can be used as an Ørsted field line to nucleate and initialize the domain wall. So our prototypes show high TMR and very minimal damage, so we can actually robustly make these devices now. So here were 6 devices that were tested of different widths. And then this is the TMR of the unpatterned film. It was 168%. And then you can see the range of the TMR we got on the pattern devices with an average of 171%. And then similarly for the RA product, 35 ohm micrometer squared unpatterned, and the range here we get 29 ohm micrometer squared, which shows we can have minimal damage to that very delicate tunnel barrier / free layer area. On the left here, just some example resistance versus field loops. Okay, so one very nice thing we can see once we have these robust devices that also now switching the spin orbit torque, so the switching current density is now low enough that we can more repeatedly switch our devices without burning them. We can now get cycling statistics of how this domain wall is switching across our devices to show that these could actually be feasible technologies. So here is the tunnel barrier resistance of that junction in the center. And here we apply 50 nanosecond voltage pulses. Every time we pulse the voltage, we measure the resistance. And so we can measure when the domain wall depends and jumps across that tunnel junction to the other side. And so we can measure that here is over 10 cycles. We've done it for 50 to 100 cycles, and we pretty reliably get around 10% cycling variation in the devices. So this is really exciting because now this is something we can put into our circuit models and actually predict how these devices would behave in application. And we can, on the left was where we reinitialized with that Ørsted field line, so all electrically, the domain wall, and switched it 10 times. On the right here, we had the domain wall go back and forth across the tunnel junction to show that we can also do a back and forth operation. One thing to point out here is a bias field was used, so this is a spin orbit torque, to allow the spin orbit torque to switch. And also the bias field is used to the field loop had some stray field that was offsetting the field loop, so to compensate for that. So that is something that needs to be engineered out, which everyone in the industry is doing a fantastic job engineering out that field for SOT MRAM. So I'm confident we could get there if we wanted to. Okay, so just a little bit about the switching current and energy if we're going to use this for an application. So these are for the 450 nanometer feature size. We got like 1 to 5 times 10 to the 7 amps per centimeter squared. So somewhat reasonable for SOT PMA devices. So if we assume the same numbers and we just assumed it would scale down to 15 nanometers, so like a very CMOS competitive feature node, then just going over to the bottom right corner here, we expect around 0.5 to 12 femtojoules of energy to operate the device. So to give some numbers to it. Okay, so let's go on. I meant to time myself, but then I didn't. How much more time do I have?
Do you have another 15 minutes?
Okay, good. So I'll set my timer now, so I keep track of myself. Okay, so let's go into one of the applications of this device as magnetic synapses So let's move on. So I already introduced these building blocks of the neuromorphic computer. So we're not the first ones to think of this idea of having this long tunnel junction on top of a domain wall track, and then depending on the position of the domain wall, we could get more than one resistance state, which can be our weights for our synapse. So here's some example papers proposing this idea. And then we can then put them into this crossbar array to make a neural network. This would be one layer of our neural network. Okay, so while we introduce the basic operations of a synapse that should have controllable weights that can be set, the actual behavior of a synapse really depends on its task. So for an inference task, we want to have a linear weight change so that we can have minimal state dependence of when we set our weight to one weight or the other. And we want symmetry so that our synapse responds equally to the positive and negative updates. And we want good control of our weights so that we can reliably reset them to, and they'll stay at the different resistance states. And then if we want to do online learning, not just inference, then we also want to think about how do we not forget data that we've learned when presented with new data, and we're trying to learn something new with our neural network. And we know that the brain accomplishes this with metaplasticity. And so that's what we want to integrate into our devices. So here is the device fabricated with the long tunnel junction on top. And we introduce notches to help more controllably set the domain wall position. So you can see now we have this long tunnel junction, and here we have 3 notches, with 2 on either side. So we should be able to get 5 resistance states out of this device. And so on the left here is what the field loop looks like. So resistance versus field. And then in the middle is what happens when we, again, have 50 nanosecond voltage pulses. And then every time we increase the amplitude a little, we check the resistance. And so we can see that we can very stably get all 5 states. Here's 1, 2, 3, 4, 5. And then the voltage, the black pulse at which it gets to those states is somewhat stochastic because the domain wall is sitting at a notch and there's some energy required to take it out, and then it moves to the next notch. So you can think of that in terms of like a state distribution versus voltage, and the probability of it being in each notch versus a given voltage. Okay, so that was the result of how our synapse is behaving. So we took our data and we applied it to the CIFAR-100 data classification test. So it's of all sorts of 32 by 32 pixel images. Okay, so we can take that data and we can back out what the conductance variation was for each of these resistance levels. And so that's shown on the right here in this error, sigma G. And then we input this into our classification test. And I'm going to skip this in interest of time, but this I'm happy to talk about the details of our neuromorphic model that we use. So how does it come out? So here is the accuracy on this particular task. And in our simulation, we can take our device data, and then we can also extrapolate to different notches or levels that we could get in the device. So the ideal is in blue here. So just the numerical result for this particular task. And our measured DW-MTJ pretty much follows the ideal very exactly. And that's because our resistance levels are very stable. So for the inference-like task, we can during the training set each synapse to each level. It's somewhat stochastic, but you can know when it's correct. And then once your neural network is trained, then you're just trying to recognize images, and it could do it very well because these resistances are very stable. So it's a nice result to show that the stability provided by this domain wall and the notches could really be beneficial for inference. So we also considered that this was for a single device measured. So if you had a network of these devices, there's going to be device-to-device variation, which is not captured in our data yet. So we also considered a worse than measured case where we included, I think, 10% variation across the devices. So then the accuracy goes down to about 60%. So to further understand how these devices would behave as a synapse, we can look to Mumax and neuromorphic, micromagnetics to explore more of the space than what we can do so far in our experiments. And so we can set up this, again, just the domain wall with a notched tunnel junction on top. And this includes 300 Kelvin, so it is including room temperature in our model. And so we can see this very linear and symmetric response we predict for this domain wall position versus time, which is really good for using it as a standard synapse. And we can characterize this in terms of these conductance heat maps, which tell us how linear and symmetric our weight updates are. So I'm going to kind of go a little fast through this, I want to get to everything. But one thing to point out from this is that if we use spin transfer torque to switch our domain wall, then it actually is very, very predictive in how it moves. And the spin orbit torque is more stochastic in how the domain wall moves from device to device. So you can see that here in this more stochastic behavior of whether the updates actually change the conductance state or not. We can also compare how this is behaving to other device types. So this is just one ramp up and down of the domain wall MTJ. Synapse using spin orbit torque. Spin transfer torque is even more linear. And this is averaged over 30 ramps up and down. And some other technologies, ReRAM in orange here is very non-symmetric. ECRAM is highly symmetric, so it's another good candidate for synapses. Okay, I'm going to skip forward a little bit because I want to get to everything in my talk. Sorry, I should have timed this better. Okay, so I'm going to skip forward all this. One thing I want to say here is that we explored then in simulation the application of this DW-MTJ synapse to this fashion MNIST task. And some things we found was that, so here's the accuracy on this task versus training epoch. And if we assume that there were no notches, but we could set our domain wall perfectly where we wanted to, which we know is going to be hard to do in an experiment, then the spin transfer torque switching is more accurate than using spin orbit torque to switch. And that makes sense because we saw the spin orbit torque switching had more noise. But we found that if we include notches, so we have a notched DW-MTJ, then spin orbit torque actually quite well outperforms spin transfer torque. So the accuracy of the spin orbit torque switching. So that was a little bit surprising for us at first, that would actually do better. And so looking a little bit more deeply into this, what's going on is that, again, here's another thing we can see is that this is the accuracy on this fashion MNIST data set. And we can simulate what it's going to be like for a different number of notches in this notched DW-MTJ type. And we can see that for spin transfer torque switching, we need to go actually quite high number of notches to get good accuracy. But for the spin orbit torque, we can actually have quite few relative number of notches and still maintain good accuracy. And so the explanation is down here that small updates that normally would fail to move the domain wall to the correct next position can do so because it's a more stochastic switch. So the stochasticity is actually aiding us, especially in the notched case. And so a nice thing about this is that, the less number of domain wall notches you need, the smaller you can shrink this device down. So it's really important to try to make it as small as we can. Okay. And another interesting direction for this research is that we know that the materials parameters can be tuned to play around with its accuracy. So for example, the length of our domain wall relative to the notch size can affect the stochasticity of this weight update. And also things like the heavy metal spin Hall angle and DMI can affect the velocity and the angle of the domain wall and can all come into play in optimizing our devices for the application. Okay. So I think maybe I have 5 more minutes. Some takeaway points so far is that we have a relatively small on-off ratio in our tunnel junctions. That's something that's always plaguing us. Hopefully those researchers working on new tunnel junction materials can someday solve this problem. But for now, our on-off ratio is modest compared to other competing technologies. But I think one of the big things that we've shown so far is that that on-off ratio actually isn't so important as long as we can show these other important properties of linearity, control, and symmetry. And those are actually hard to achieve with some of these competing technologies. And as I said, the notches plus spin orbit torque provides this without needing to sacrifice too much area of our device. Okay, so so far we've really focused on the ideal synapse behavior for inference. What about for when we want our neural network to be learning? And here's this problem of wanting to learn and not forget previously what it learned. And so what we can do is simply take our same device, but now make it trapezoidal in shape. So here's the SCM image within the notches, and the domain wall can move across the track again. And now it's going to behave a little different than before. So here's the field loop on the left, and here is our resistance of our tunnel junction versus voltage pulses of increasing amplitude. And now we no longer get a stochastic behavior, we get a more deterministic behavior. Here we had three levels. So if you look back at our SEM image, these notches were not all the same depth. And so some notches are being skipped. And so that is something we need to work on to really resolve all the weight levels consistently. But we can definitely see this behavior of that over many cycles. We can, at very similar voltages, hit these three notches. And that's quite different than before, where it was much more random. We also see this asymmetry come out in the direction that we apply our voltage pulses. So we can move the domain wall one way, up the ramp, and then back. It just takes one higher voltage to switch it back. And so that can have its benefits depending on the application. Okay, so we can take this device and again, let's apply it to our neural network simulators and see how it behaves now. So we can define a metaplastic function, F meta, which will help us to characterize this asymmetry of the domain wall response across the wire. So it's a function of this weight that represents the domain wall position, and then the widths of our trapezoid between the bottom and the top. Here, our trapezoid was a 1:4 ratio. And so you can think of it as this F meta would just be 1 for our linear synapse that we characterized earlier. And then it has this kind of behavior that matches these different conductance states versus voltage of the trapezoidal version. Okay, so here we knew this would do better on a particular type of task, a stream learning task. So in this task, we're actually binarizing the weights themselves. And what we did was we have the fashion MNIST data set, and we are introducing subsets at a time for it to train on and then to do inference on. So we have 60,000 images, and we split them into 60 subsets, and we show them to the network 30 epochs at a time, like that. So new data is coming in that it's learning on, and we're trying to see if it doesn't forget the old data. And so this is just details of what it looks like. I'll skip over that for now. So what we find is, I think it's a pretty interesting result. Here is the accuracy versus subset presented to the neural network made out of these devices using the data put into the simulator. And so first of all, these ticks up here are for when the full data set is first trained on, and then we just look at the accuracy. So it makes sense that for the full data set, the linear synapse that we showed before, just a straight domain wall track, did the best with highest accuracy. And if we had a trapezoidal shape to our track, it actually did worse. But it's opposite when we do this stream learning task. So here, the trapezoidal device has much higher accuracy and learns much faster than our linear device. So this is really exciting. It shows that by tuning the device geometry, we can make our synapse better for this type of stream learning task. Another thing that's really nice to see here is that if you look at the accuracy versus subset introduced to the neural network, we can look at a linear synapse with 32 notches, so this is shown here, versus a trapezoidal with only 4 levels, and they perform the same. So now we can really shrink down our device from looking like this to just looking like a simple, really small device like this, which is really nice for seeing this in application. Okay, I'm probably out of time now, right? One more minute? Okay,
1 minute.
I will, 1 minute, it's okay. I'm just gonna, you can read the paper on this. So this paper just came out in PNAS Nexus, so it'll be out soon. And we, in simulation using MuMax, we looked at a completely different system for neuromorphic computing, which is this small array of oscillating skyrmions. I think the takeaway message here is just that I think domain walls are really good for moving a spin texture around in a track. And skyrmions can be used for that, but they also have their own challenges in that application. Skyrmions have nice resonant behavior, though, that is really harder to achieve in domain walls. So that was our goal here, is trying to take advantage of the resonant behavior of skyrmions, and then the fact that they can be manipulated by multiple inputs. So here we have current can go through each of these strips and change the position of the skyrmions, and then based on their position, they're going to resonate differently in response to this antenna that can be putting in other data. So I think one of the big things that we're really looking for here is like we can take advantage of the richness of our physical system, that it can respond to more than one input. And so skipping to the point then about this, so we did a lot of simulations in MuMax, again, on this oscillatory, these neurons, and we can think about how they behave. And then we can take these skyrmions, looking down at a snapshot of the MuMax simulation. We can put them in different configurations, and then they're going to have different oscillatory behavior versus field. And so we can think of those as two different transfer functions of a neuron. And then we can apply that. And in this case, we applied it to breast cancer diagnosis. So we have our context information, which comes in as our modulatory input. And then we have our images of our cancer cells that come in as our direct input. And we can use the context to better characterize whether it's cancerous or not. So I'm going to skip to the end of my talk. You can read it here. In conclusion, I have a long conclusion here, but I hope that I've imparted to you our recent work on using magnetic materials, domain walls, magnetic tunnel junctions, and skyrmions as a rich physical space for computing, including for synapses and for neurons. And brief acknowledgement, these are all the nice faces of the people I introduced at the beginning, and our funding from the National Science Foundation and from Sandia National Labs. I'll end there for questions.
Thank you so much, Jinan, for a very inspiring talk, actually. And with this, I would like to open the floor for any questions. If there are no questions, yeah, I can ask a very quick question. I'm curious if you think there's going to be any type of interference or issues with the geometry once you start to have a larger density of these devices, right? Because this computation is very extremely influenced by the geometry. So I wonder, once you have to put this trapezoidal together, what might happen?
Yeah.
So
yeah, that's a great question, and we're something that we've explored a little bit, but want to explore more. So we looked at, we didn't look at the trapezoid ones, we just looked at the straight ones. If you had like straight domain wall tracks acting as, in this case, neurons, so like your domain wall's moving, that's integration, they pass the tunnel junction, that's firing, and then you densely put them close to each other, there's going to be magnetic straight field interactions. Right. And so I can send you the paper. It actually was really interesting because we saw this at first in very narrowly spaced wires that are like 6 nanometers apart, but it actually was, in simulation in MuMax, it was helping us. One domain wall would start to get ahead of the other one, and it would actually slow down its neighbor. And so this is something called a lateral inhibition that's seen in the brain, where, yeah, you can suppress the neurons that shouldn't fire, and you can have the neurons that should fire. So then we did some simulation work. It was really interesting. I don't know yet if it's going to be physical to make, because what we found was that it actually is that one domain wall stray field was affecting the angle of the other domain wall, because the domain wall actually has an angle until it goes to Walker breakdown, right? And that was affecting the efficiency of the next one, how efficient it would move. So there's definitely really interesting inter-device interactions, and I think that's a whole other thing we can be taking advantage of and better understanding, for sure. Yeah.
I think there are 2 more questions in chat.
Great. I see them. Let me see. Okay, so someone's asking, May, hi May, are the notches on the DW-MTJ for generating and controlling domains? Could you elaborate on how they work And do the sizes of the notches matter relative to the wire width? Yeah, so the notches we introduced because it is a little bit hard to get a domain wall to perfectly stop at a certain spot in a wire. Anyone who's worked with domain walls knows that. So the notches are very helpful, as you saw in the data. With the notches, we can reliably have the domain wall stop where we want it to. So that's why we introduced the notches. And the size does definitely matter. And that's another knob we can tune. So depending on the size, and you can think of it relative to the domain wall length. So that's kind of the size that matters. But the domain wall length is related to the wire width. So yes, it's relative to the wire width too. And then the second question is, great that the trapezoidal design fared better than the linear device design, compressing the devices. Could I ask what factors allowed for this? Yes, I went through that really fast. Sorry about that. So the main thing that allowed for this is that with the trapezoidal design, we can have different voltages set the domain wall to different notches. So we can then, for example, have the higher voltages encode more important information, and then that are harder to change. And then the lower voltages can encode less important information about the images that could change. So we kind of have this non-linearity to what voltages we can use and how easy it is to change that weight once it's set. And so that's really what we're using here. And I think there's a lot of other ways you could probably accomplish that in a physical system. What temperature can the skyrmions be observed in the TMIG structures for T-SKONE? Yeah, this is a very astute question. So this was done in UMax only. So I know from what I understand of the experiment so far of platinum TMIG, it's slightly above room temperature that the skyrmions are being observed in that material. We picked it because the skyrmions can be quite small in that material, so that's why we were using it. So you might need to have a different material to really operate at room temperature. It's just slightly above room temperature, but we did have temperature in that simulation. And we did look at the stability of the skyrmions as one thing the reviewers asked for, was look at the stability as they just sit in these little pinned regions. Okay, the next question by Matt. Yeah, no problem, May. I think you said this, but for your network training, did you do write then read to verify that stochastic devices actually change state, or does your learning algorithm account for the stochasticity? For the training, it was all simulation based on the device data. So we didn't yet have to have any specific scheme for that. We could just assume that we can set the device to a certain level. So that would be the next step to do actual arrays in experiments. Yeah. And then Michael said, for the CIFAR-100 and this test, it seems that the accuracy flattened out after about 32 levels. Why is this? Oh, that's a really, really good question. I should ask Sam next for the question who's here, but from what I understand, you have a certain number of levels to get that matter. So a certain number of weights is useful to get a certain amount of accuracy for a given neural network, and 32 is a common number that's used. So you don't need just, usually there's a certain number of weights, we have enough, and you don't really need much more than that. Is that what you would say, Sam? Yes. Sam was one of the main authors on the paper, so yeah.
Good. If there are no more questions, let's thank Junan again for that great talk. And with this, we reach to the end of our conference. So it's my time to give a few closing words. Thanks again, Junan. I'm actually going to share screen now for a second.